Okay, suppose we have a sequence of numbers. If we're programming this on a computer, we can just create an array, and then access the index of that array to get that element back. But suppose we wanted to challenge ourselves and come up with a function that encodes this sequence. Could we create a function that when you put in the index gives you back that sequence number? And let's not cheat here. We're going to limit ourselves to only arithmetic functions and some extra stuff. Plus, minus, times, divide, and let's say the derivative as well. One thing that we could do is tag each number of the sequence with an unlike or linearly independent term, such that when we add them all together, they won't combine. So we arrive at this polynomial here, but suppose we wanted to get term n back. How would we go about doing that? Well, for any polynomial, if we plug in 0 for x, it'll delete everything to the right of the constant. And if we take the derivative of the polynomial, it'll essentially shift all of the elements to the left. And we can keep doing this as well, but we see we keep accumulating some extra factors as well, which we need to get rid of. And if we keep doing this process, we'll see that there is a pattern to this accumulation. Here, a4 is being multiplied by 4 times 3 times 2 times 1, and that's just 4 factorial. We'll see the same holds for 5, 6, and n in any general case. And now we know that we can just plug in 0 for x, and now we have a way of shifting the array, or I guess in this case the polynomial, to the left and deleting everything to the right, so we can always get that constant term back that we want. So if we encode our sequence onto a polynomial, all we have to do is take the nth derivative, evaluate at x equals 0, and divide by n factorial, and we'll get that element of the sequence back. This property of encoding sequences onto polynomials is why in number theory it's called an ordinary generator function, and with a name like that, you know it has to be pretty important to the subject. So now that we have a new tool in our mathematical tool belt, let's have some fun with it. So we all know what a polynomial looks like on the integers and on the real numbers, but have you ever seen a polynomial on the complex plane? Let's see if we can predict how it'll behave. If we look towards the end of the series, we can model that last term in the series, quote unquote, as the limit as n goes to infinity of x to the n. We see that if the absolute value of x is greater than 1, it'll diverge, meaning that we won't have an answer there that we can plot. But if the absolute value of x is less than 1, that'll tend towards 0, which we know how to deal with. So if we plot our polynomial on the complex plane, we'll see that it draws out this circle, where the absolute value of x is equal to 1. Everything outside of it won't be defined, and everything inside will, given that our sequence isn't infinite at any term. So now here's our game plan. If we break our image down into an x direction and a y direction, we can use those values to define a complex number. We can plug that complex number, along with our sequence, into our generator function and get a new complex number out. We can then take the amplitude and phase of that new complex number to determine the color of the pixel that are in the x and y pixel locations on our image. So let's move on to the programming. Okay, so here we are in a Jupyter notebook running Python. First, we're going to have to import some math libraries and some imaging libraries. Next, we'll use the math we learned to define our ordinary generating function. Next, we'll define our color function. And then a function to plot the generating function. Try the run, and then debug our code. And would you look at that? Looks pretty cool. That was sine, and this is tangent. And hey, I'll even make a function that turns a string into a repeating list of numbers so that we can put that into our function as well. So now that we have these images, what can we do with them? I think I like the tangent the best, so I'll do something with that. Here I'm feeding the tangent generating function image into a CNC paper cutter software. And here's the paper cutter cutting those shapes out of a piece of cardstock. Use our cutouts as spray paint stencils. Stick it on the wall and boom! That's how you make tangential art. Thanks for watching.